In the last lecture, we had gone through a physical interpretation of the meaning of convection and diffusion. Convection is transport of material or energy or even momentum along with the fluid flow. Okay, so, I illustrated that in the last lecture by looking at a surface within the fluid, okay, a surface within the fluid, and if there is a flow velocity, then as the fluid flows across the surface, there is going to be material transported from one side of the surface to the other side of the surface. The transport depends only upon the velocity perpendicular to the surface, because the velocity parallel to the surface does not cause any transport. If we consider a time interval delta t, then the volume that is transported across the surface within a time delta t is equal to the velocity perpendicular to the surface times delta t. Okay. Therefore, the mass transported is going to be equal to the volume transported times the concentration or the mass density, and that is equal to the concentration times V n times delta t times delta s. Okay. The volume is delta s times the thickness is V n times delta t, and therefore, the mass transported is C V n delta t into delta s. Flux locally is defined as mass transported per unit area per unit time, and that is going to be equal to the concentration times V n. So, the flux across a surface is going to be the local value of the density, concentration for mass flux, energy density for energy flux, momentum density for momentum flux. Density times the velocity perpendicular to the surface. And I should note here that in the limit as delta s goes to 0 and delta t goes to 0, the volume transported across the surface goes to 0. The flux is finite, okay, because it is the ratio of the concentration times volume divided by the area divided by the time interval. Okay. So, this flux remains finite in the limit as delta s goes to 0 and delta t goes to 0, and it is uniquely specified at each point for a given surface orientation. Okay. For a given surface orientation, you have to find what is the velocity perpendicular to the surface, and from that you will know what is the flux across the surface for fluid convection. The diffusive flux due to fluid diffusion is due to the molecular velocity fluctuations, not the fluid velocity fluctuations. And we defined it as the transport per unit area. Flux between two surfaces is the transport per unit area, okay, across a fluid layer of thickness delta z in this case. And if you impose a difference in concentration delta c across that thickness delta z, there is going to be a flux across. That flux is proportional to delta c, inversely proportional to delta z. The constant of proportionality is the diffusion coefficient, and if you express the flux in this form, okay, I should note here that in the limit as delta z goes to 0, right, in the limit as delta z goes to 0, right. So, this we had solved originally for a difference in concentration and for a difference delta z. In the limit as delta z goes to 0, right, the flux we had said was equal to J is equal to minus d delta c by delta z. Okay. In the limit as delta z goes to 0, delta c will also go to 0 in such a way that that ratio is a constant. Therefore, the diffusive flux is also a constant as you take the thickness or the volume of that differential area down to 0. The concentration difference will also decrease to 0 and the flux will be finite. And so, the flux of any quantity can be written as the negative of the diffusion coefficient of that quantity times the difference in density divided by the thickness. Okay. And just by dimensional analysis, the diffusion coefficient has dimensions of length square per time. For mass diffusivity, the diffusion coefficient is just the mass diffusion coefficient, dimensions length square per time. Thermal diffusivity, the diffusion coefficient is k by rho Cp. K is the conductivity, rho the density, and Cp the specific heat. This also has dimensions of length square per time. and for momentum transport the flux is the momentum diffusivity, viscosity divided by density, dimensions length square per time. So, once we have these definitions of the flux, we can create dimensionless groups. Velocity has dimension length per time, diffusion coefficient has dimensions length square per time. Therefore, the velocity times the characteristic length divided by the diffusion coefficient is a dimensionless number. That is the ratio of convection and diffusion. Okay. For mass, it is a Peclet number, the velocity times the diffusion coefficient, the characteristic dimension divided by the mass diffusion coefficient. For energy, it is a Peclet number for energy transport, the velocity times the length scale divided by the thermal diffusion coefficient. For momentum, it is the Reynolds number, velocity times length scale divided by the kinematic viscosity or momentum diffusivity. Okay. And you can also define Prandtl number and Schmidt number and Lewis number as the ratios of two different kinds of diffusivity. Okay. Prandtl number is momentum by thermal diffusivity, Schmidt number is momentum by mass diffusivity, and the Lewis number is thermal by mass diffusivity. Okay. And these are the independent dimensionless group that we had encountered earlier. The dependent dimensionless group is the dimensionless flux. The Sherwood number, the flux divided by, if you recall, the right side of the quantity having the same dimension as the right side of Fick's law, d delta c by the length scale. The Nusselt number is the average flux, heat flux divided by k delta t by the length scale, and conventionally the dimensionless momentum flux is scaled by the inertial scales. In this case, it is a shear stress momentum flux divided by the average kinetic energy per unit volume. So, before proceeding to look at correlations for these, let us first discuss a little bit about what are the characteristic length scales and what are the characteristic velocity scales for different configurations, both for internal flows as well as for external flows. Okay. A typical internal flow is the flow through a pipe. Okay. A pipe of length L and diameter d. Okay. Okay. And for this flow through a pipe, of course, it is quite easy to justify the characteristic velocity scale as the average velocity. Okay. Average velocity is basically the ratio of the flow rate and the cross sectional area of the pipe. Okay. So, V average is the characteristic velocity scale and d, the pipe diameter, is the characteristic length scale. Okay. This in internal flows, usually the length of the pipe L is much larger than the diameter, the pipe diameter. Okay. What would you do if the pipe does not have a circular cross section? Okay. How do you define the characteristic length scale in this case? Okay. The way it is defined for internal flows is to define something called a hydraulic radius. Okay. The hydraulic radius is basically the cross sectional area, okay, divided by the length of the wetted perimeter. Okay. The wetted perimeter is the perimeter of the pipe that is wetted by the fluid. Okay. Okay. So, for a circular pipe, for a pipe of circular cross section, this wetted perimeter will be a circle. Okay. The hydraulic radius is defined as the cross sectional area divided by the wetted perimeter. If you had a rectangular pipe, for example, the cross section would be a rectangle, and the wetted perimeter will be the sum of the sides of the rectangle. The cross sectional area will be the cross section of the rectangle. Okay. So, you take the cross sectional area and divide it by the wetted perimeter, and that is the hydraulic radius. Okay. For a circular pipe, okay, you know that the cross sectional area is pi d square by 4 and the wetted perimeter is pi d. Okay. The perimeter of a circle is pi times the diameter. Okay. Cross sectional area is pi d square by 4. Okay. So, this is effectively d by 4. Okay. And if you had a rectangle, for example, of width w and height h, then the cross sectional area will be equal to w into h. Okay. So, if I had a rectangle of width w and height h, w into h will be the cross sectional area, and the wetted perimeter will be 2 into h plus w. Okay. The sum of all 4 sides, the sum of the lengths of all 4 sides of this rectangle. Okay. And once you have calculated this hydraulic radius, the equivalent diameter, okay, is defined as 4 times the hydraulic radius. Okay. Okay, not 2 times, this is defined as 4 times the hydraulic radius. This will be equal to the diameter for a circular pipe. Okay. Okay. So, for an internal flow, this is the characteristic length scale. The characteristic velocity scale in all cases is equal to the average velocity, the ratio of the flow rate and the cross sectional area. Okay. The average fluxes, okay, are basically defined as the total transport rate by the total surface area. Okay. Is defined as the total transport rate divided by the total surface area, which is equal to the total transport rate divided by the wetted perimeter times the length. Okay. Wetted perimeter is the length of the perimeter of the cross section times the length gives you the total area for transport. Okay. Okay. Now, for an external flow, okay, a flow past an object or something like that. Okay. If you know that if you have a circular object, right, you can easily define what is the characteristic length scale. That is just the diameter of the object. Okay. The characteristic velocity scale is what is called the free stream velocity. Okay. So, if the object is moving relative to the fluid and the fluid is stationary at infinity, right, the characteristic velocity is the velocity of the object relative to the fluid far away. Okay. It is called the free stream velocity. Okay, it is called the free stream velocity, the velocity far from the object. Okay. I should recall, I should note here that the wall shear stress is also defined in a similar way. It is the total transport rate of momentum to the surface divided by the total surface area. So, the average fluxes, whether for mass, momentum and energy for this external flow, are defined in exactly the same way. Okay. So, back to our external flow. Okay. V free stream is the free stream velocity and d is the diameter of the object. For a spherical object, there is only one length scale. What happens if the object is not spherical? Okay. In that case, once again, for an external flow around an object, we can define the hydraulic radius as not the area by the length, but rather the volume by the area. Okay. It is going to be defined as total volume of the object divided by the surface area of the object. Okay. So, for example, for a spherical particle, the volume is pi d cubed by 6 and the surface area is pi d square. For those of you who are more comfortable seeing this in terms of the radius of a sphere, the volume is 4 by 3 pi r cubed, and if you substitute r is equal to d by 2, you get pi d cubed by 6, and the surface area is 4 pi r square, and if you substitute r is equal to d by 2, you get pi r square, which is equal to d by 6. Okay. And the characteristic length equivalent diameter, which is the characteristic length for this case, is defined as 6 times RH for 3-dimensional objects. Okay. It is defined as 4 times RH for 2-dimensional cross sections, 6 times RH for 3-dimensional objects. So, that this will be equal to the diameter for a spherical particle, and the characteristic velocity is the what I call the free stream velocity. Okay. Typically, you would have either the particle moving relative to the fluid, as in the case of a particle settling in a fluid, for example, or an object falling in air, and in that case the fluid far away is at rest, and at the surface of the object you have a certain velocity. The difference between the surface velocity and the fluid far away is the free stream velocity. If you had fluid flow past an immersed object, for example, if you had flow in a fluidized bed or something like that, then the particle is on average stationary, the velocity is 0, but the fluid away from the particle is moving with a fixed velocity, and that is the free stream velocity. Okay. So, in these cases also, right, so you define the Sherwood, the Nusselt number, the Sherwood number, I am sorry, the Peclet number and the Reynolds number based upon the free stream velocity and the equivalent diameter. Okay. So, in internal flows, the Reynolds number and Peclet number will be defined as V free stream, right, times the equivalent diameter divided by the diffusivity. Okay. This could be either mass diffusivity, thermal diffusivity, or momentum diffusivity. Okay. That would be the definition. Okay. Whereas for internal flows, you would use the average velocity. Average velocity times the equivalent diameter divided by d alpha nu. Okay. The average mass and heat flux in this case are defined for flow past objects QAV and JAV are defined as the total transport rate divided by the surface area. Okay, these are the definitions of the fluxes. Okay. And once I have the definition of the flux, you can define the Nusselt number or the Sherwood number as the average flux divided by d delta c by the equivalent diameter, or k delta t by equivalent diameter. Okay. The average momentum flux is defined slightly differently because the momentum is a vector. Okay. It has a direction associated with it. Okay. So, therefore, if I have an object that is moving relative to a fluid, okay, the net force on the object due to the pressure difference between the front and the rear. Okay, let us say that I had a pressure difference between the front and the rear hemispheres of the object. The force exerted is going to be equal to the pressure difference, I am sorry, the force exerted will be the pressure difference times the projected area, okay, not the surface area. Okay. The pressure difference will be the force will be the pressure difference times the projected area, the area of the object that is projected perpendicular to the flow. Okay. The pressure of the area of the object that is projected perpendicular to the flow. Okay. Therefore, in this case I have to define the friction factor, for example. Okay. Friction factor in the case of the flow past a pipe, we had defined it as the wall shear stress divided by the kinetic energy per unit volume, the average kinetic energy per unit volume. In this case, the friction factor, it is not the friction factor, it is what is called the drag coefficient, okay, is defined as the drag force divided by the projected area. Okay, is defined as the drag force divided by the projected area, right, divided by half rho V free stream velocity square. Okay. So, it is defined as the ratio of the drag force in the projected area, okay, not the drag force in the total surface area of the sphere. Okay. Okay. So, therefore, only for momentum transport you have to recall that in the case of the drag coefficient for the flow past objects, you have to take the ratio of the drag force and the projected area, not the drag force and the total surface area of the sphere. Okay. Whereas, in the case of transport in a pipe, for example, okay, in a pipe, for example, the friction factor is defined as the wall shear stress, okay, divided by half rho VAB square. Okay. So, that is one major difference. Okay. The other kind of configuration that you might come across is flow past a flat plate. Okay. A flat plate of length L, okay, and of infinitesimal thickness, okay, and of infinitesimal thickness across which there is a flow, okay, and there could be either mass transfer or heat transfer in this flow past a flat plate. Okay. In this case, for heat and mass transfer, for example, the flux will be defined, and let us assume that this plate had some width W in the direction perpendicular to the flow. Okay. Let us say the width was W. So, you had a flat plate, length L along the flow direction, streamwise direction, and width W perpendicular to the flow, with in which there was an infinitesimal thickness, so that there is very little blockage of the flow due to the presence of this plate. Okay. In contrast to a sphere settling, for example, where the sphere presents a substantial blockage to the flow, due to which the fluid flow has the streamlines have to curve around the object. Okay. Due to which the fluid flow streamlines have to curve around the object. Okay. So, these are what are called bluff bodies, and at high Reynolds number, the drag force in these cases is because of the pressure difference between the upstream and the downstream hemispheres. Okay. In contrast, for these kinds of slender bodies, which for which the projected area is very small, in that case most of the force exerted on the object is due to the shear stress acting at the surface of the object. Okay. Most of the force on the object is equal to the shear stress acting at the surface of the object. Okay. In this case, because the projected area is infinitesimally small and the major contribution to the force arises from the tangential stress, the what is called the skin friction factor, okay, the dimensionless momentum flux, the skin friction coefficient, is defined as the drag force divided by the tangential surface area, okay, divided by half rho V free stream square, where V free stream is once again the velocity of the fluid relative to the object far from the object. Okay. So, in this case you divide by the tangential surface area that is parallel to the flow for a slender object when you define the skin friction coefficient. Okay. Whereas, the drag coefficient for bodies which substantially block the flow, okay, where the projected area is comparable to the size of the object, in that case you divide it by the projected area. Okay. So, that is the difference. In this case, the length scale is the length of the plate, okay, because the dimension perpendicular to the flow is infinitesimally small. Okay. The velocity is the free stream velocity. Okay. The average fluxes for other quantities, for momentum and for mass and energy, is the total transport rate divided by the total area of the surface, okay, surface area, okay, which is basically total transport rate divided by L into W. Okay. Okay, that is how it is defined for a flat plate, for example. Okay. The Reynolds number is defined as V free stream into L by nu. Okay. The Peckley number is defined as V free stream into L by alpha, alpha the diffusion coefficient. Okay. And the fluxes are defined based upon the total area, and the skin friction coefficient is also defined based upon the total area of the surface that is parallel to the flow. Okay. Only for the case of a three-dimensional object which is blocking the flow, the momentum flux is defined based upon the projected area. Okay. So, these are the definitions of the characteristic length, velocity scales for different kinds of flows. Internal flows, length is equivalent diameter, velocity is average velocity. External flows, the length if for mass and heat transfer is the equivalent diameter. Okay. For mass and heat transfer is the equivalent diameter. Area is the surface area of the object, okay, and the velocity is the free stream velocity. For flat plates, the length is the length of the plate in the streamwise direction. The velocity is once again the free stream velocity far from the object, and the area is the tangential surface area parallel to the flow, okay, for a flat surface. Okay. So, these are the dimensionless the definitions of the dimensionless groups in different configurations. Okay. So, we have looked at ratios of convection and diffusion, ratios of different types of diffusion. Okay. You can have other dimensionless numbers. Okay. For example, you can have dimensionless numbers that involve surface tension. Okay. Surface tension, I will use here the symbol gamma. Okay. And recall that in one of the earlier lectures we had got the dimension of surface tension as mass times T to the minus 2. Okay. So, based on this I can get dimensionless ratios of viscosity and surface tension and inertia and surface tension quite easily. The capillary number is the ratio of the viscosity and the surface tension, mu times the characteristic velocity by gamma, okay. And the Weber number is the ratio of inertia and surface tension. It is defined as rho v square, okay, times the equivalent diameter by gamma. Okay. Or I will use here the characteristic length. I will use LC for characteristic length and VC for characteristic velocity. VC will be average velocity for internal flows and free stream for external flows, and LC is the equivalent diameter or the length of the flat plate for external flow. Okay. And similarly, you could also have dimensionless ratios of gravity and for example, inertia and gravity for example. The Froude number is defined as Vc Lc by G. I am sorry, I should root of G Lc, okay, where G is the acceleration due to gravity. You know that G has dimensions of length L T to the minus 2, and you can verify that the velocity divided by square root of gravity into length is dimensionless. That is the ratio of inertia and gravity. Okay. You could have a ratio of gravitational and surface tension. It is called the Bond number. Okay. This is rho G L C square by gamma. Okay. Okay. Rho G into L C square by gamma, you can verify that it is dimensionless. Okay. And there are other dimensionless groups that you could have. Okay. And you can verify that is also dimensionless. Similarly, you can have ratios of viscosity and surface tension and various other things. Okay. So, just based on dimensional analysis you can get all of these effects. Okay. So, I have given you a brief introduction to dimensionless groups as ratios of different kinds of effects, how they are defined, what are the length, velocity, scales in different internal and external kinds of flows, and how you would define the average fluxes based upon the surface areas for mass, heat and momentum transfer. And in the next lecture onwards, we will take a closer look at different kinds of flows, the momentum transfer in different types of flows. Okay. We will start with an internal flow, the flow through a pipe, and then progress to flow past a flat plate and flow of an object in a fluid. Okay. And we will examine each of these individually, their characteristics and what are the kinds of correlations that are used for describing these kinds of flows. We will continue this in the next lecture. Thank you.